Lesson Techniques for Explaining AI Outputs. Explaining AI outputs is a critical component of ensuring transparency and accountability in artificial intelligence systems. As AI becomes increasingly integrated into various sectors, the demand for comprehensible and justifiable AI decisions has surged. This necessity is not just a technical challenge, but a moral and ethical imperative, particularly in high-stakes areas such as healthcare, finance, and law enforcement. The ability to effectively elucidate AI outputs can mitigate risks, foster trust, and facilitate compliance with ethical standards and legal regulations. One of the foremost techniques for explaining AI outputs is the use of interpretable models. Interpretable models, such as decision trees and linear regression, provide a clear view of how input data is transformed into output predictions. These models inherently offer transparency because they allow users to trace the decision-making path. For instance, decision trees are structured in a way that every decision node is a clear if-then rule, easily understandable by humans. This transparency can be particularly beneficial in sectors like finance, where regulators demand clear justifications for decisions such as loan approvals or credit scoring. A practical implementation of decision trees can be seen in credit risk assessment, where each branch of the tree represents a decision rule based on the applicant's credit history, income, and other relevant factors. However, not all AI models are inherently interpretable. As more complex models like neural networks and ensemble methods gain popularity, the challenge of explaining their outputs increases. For these models, post hoc explanation techniques become essential. One such technique is the local interpretable model agnostic explanations, which approximates complex models locally with interpretable models. LIME provides explanations by perturbing the input data and observing the changes in predictions. This method is useful in scenarios where understanding the contribution of individual features to a prediction is crucial. For example, in healthcare diagnostics, LIME can help doctors understand why a particular AI system has diagnosed a patient with a specific condition by highlighting which features were most influential in the decision. Another effective tool for explaining AI outputs is Shapley additive explanations. SHAP values offer a game-theoretic approach to explain the output of any machine learning model. The core idea is to calculate the contribution of each feature to the final prediction by considering all possible combinations of features. This method provides a unified measure of feature importance, ensuring consistency and fairness in feature attribution. In practice, SHAP can be applied in sectors like insurance, where understanding the factors influencing policy pricing or claims approval is necessary for both compliance and customer satisfaction. By using SHAP, companies can justify to customers and regulators how specific attributes, such as age or health conditions, impact their premiums. In addition to these techniques, visualization plays a pivotal role in explaining AI outputs. Visual tools like heat maps, partial dependency plots, and feature importance graphs can help stakeholders intuitively grasp complex data patterns and model behavior. For instance, heat maps can be used to visualize the attention weights in neural networks, highlighting which parts of the input data were most influential in making a decision. This approach is particularly valuable in image recognition tasks, where understanding which parts of an image contributed to the classification can aid in both model validation and user trust. Frameworks for explaining AI outputs also emphasize the importance of context and audience. Different stakeholders require different levels of explanation, from technical details for data scientists to high-level summaries for executives or end users. The DARPA's Explainable AI program underscores this by advocating for explanations that are not only accurate and detailed, but also comprehensible and actionable for the intended audience. This involves tailoring explanations to match the cognitive and technical expertise of the users, ensuring that they can make informed decisions based on the AI's outputs. Furthermore, the practical implementation of explanation techniques requires a systematic approach. One effective framework is the CRISP-DM model, which can be adapted to include explanation stages. This involves 1. Business understanding, defining the purpose of the AI system and the need for explanations. 2. Data understanding, identifying which data features are crucial for explanations. 3. Data preparation, ensuring that data is clean and relevant for generating meaningful explanations. 4. Modeling, selecting interpretable or explainable models. 5. Evaluation, assessing the quality and comprehensibility of explanations. And 6. Deployment, integrating explanations into the AI system's workflow and making them accessible to stakeholders. To illustrate the effectiveness of these techniques and frameworks, consider the case study of an AI system used in a bank for approving loan applications. Initially, the bank utilized a complex neural network for predictions, which led to customer dissatisfaction due to the lack of clear explanations for denied loans. By implementing Lime and SHAP, the bank was able to provide detailed and understandable explanations for each decision, highlighting factors like credit score, income stability, and debt-to-income ratio. This transparency not only improved customer trust, but also ensured compliance with regulatory requirements for fair lending practices. Moreover, by using visualization tools, the bank's executives could better understand the model's behavior, leading to more informed strategic decisions. In conclusion, the techniques for explaining AI outputs are multifaceted, involving interpretable models, post hoc explanation methods, visualization tools, and tailored communication strategies. By leveraging these techniques, professionals can enhance the transparency and accountability of AI systems, ensuring they are both ethically sound and legally compliant. The integration of explanation mechanisms into AI systems is not merely a technical necessity, but a cornerstone of building trust and fostering broader acceptance of AI technologies in society. As AI continues to evolve, the demand for robust explanation frameworks will only grow, making it imperative for practitioners to stay informed and adept in these methodologies.